Welcome back. Today, we're skipping the fluff and diving right back into the core of our flow measurement series. In this explainer, we're unpacking two absolutely critical concepts: flow meter rangeability and a totally non-negotiable installation rule. Honestly, if you ignore this rule, it's going to ruin your process control before it even starts. So let's get right into it. Okay, let's kick things off by doing a super quick recap of our last explainer. Remember, we basically have two main families of flow meters. On one side, we've got energy extractive meters. Think of your standard orifice plates. These force fluid through a restriction to create a readable pressure drop. They literally steal energy from the system to get a reading. Then on the flip side, we have energy additive meters, like mag meters. These barely even touch the flow. They act a lot more like a radar gun on the side of a highway, generating just a tiny voltage as a conductive fluid moves through a magnetic field.
But hey, knowing how a meter measures flow, that's really only half the battle. You also have to know exactly when it can measure accurately. And that brings us to rangeability. Basically, rangeability is just the ratio between the minimum and maximum controllable flow that a meter can accurately measure. We all tend to get hyper-focused on a meter's accuracy at its absolute maximum design flow, right? But understanding its accuracy at the lowest limits of your process is just as important, if not more so.
And this brilliantly illustrates the massive gap in capabilities between the two. See, while energy extractive meters are super rugged and, really well understood, they have notably low rangeability. We're talking typically only a 4-to-1 ratio. They just can't measure accurately much below 25% of their calibrated max flow. Compare that to the vast adaptability of the mag meter, which maintains its linearity across a much, much wider spread of flow rates. Let's ground this theory in a real-world scenario. So you've got an orifice plate that's perfectly accurate at your plant's normal design flow. Great, but what happens during a plant turndown? If operations drop to, say, 15% of your maximum calibrated flow, that orifice plate falls completely into a blind spot. It becomes practically useless, exactly when you might need that reading the most to keep the plant stable. So rangeability, not just top-end accuracy, is often the ultimate deciding factor when you're specifying a meter. Moving right along to Section 1, the rules of the game for magnemeters. Now, mag meters are incredible, but man, they are demanding. Here are their totally non-negotiable requirements. Number 1, you must have a conductive fluid. Number 2, the pipeline has to be completely full. And number 3, the meter piping itself must be manufactured from a non-magnetic material, like stainless steel, and internally lined with an insulating material. Why? Well, because the whole principle relies on generating a magnetic field and detecting a voltage across the flow. Without that insulating liner, the conductive pipe wall would just short-circuit the electric field and you'd get absolutely zero data. Which brings us to a pretty stark warning. If your fluid is non-conductive, a mag meter will not work, period. You literally cannot specify a mag meter for pure substances, gases, or most organic chemicals and hydrocarbons. It honestly doesn't matter how perfectly it's installed or how flawlessly you ground the flanges, the physics simply aren't there to generate the voltage. It's a non-starter. Now, what's really wild here is the sheer financial weight behind making this mistake. Specifying a mag meter for a non-conductive hydrocarbon stream is hands down one of the most expensive instrumentation errors you can make at the specification stage. Think about it. It means buying a high-end, premium sensor, paying to install it, discovering you're getting zero readings, and then having to physically pull the whole thing back out of the line to replace it. It is a brutal, costly lesson in fluid properties. I actually want to pause and challenge you for a second here with an interactive moment. Think about a produced water pipeline running on a gravity feed. The water's highly conductive, right? So you specify a mag meter. Perfect. But what happens to your reading if that pipe is only half full during a low-flow plant startup? What is that meter actually telling the folks in the control room?
So the crucial point is that your reading becomes completely unreliable. Here's why. Mag meters calculate volumetric flow based on the velocity of the fluid crossing that magnetic field. And that velocity to flow calculation inherently assumes that the entire cross-sectional area of the pipe is completely full of liquid. If it's only half full, the math just breaks. You'll get a totally false, potentially dangerous reading. This is exactly why mag meters absolutely must be installed with sufficient back pressure or in specific pipe tips to guarantee they run full 100% of the time.
Okay, let's tie this all together and summarize our core takeaways into a clear decision tree. When you're evaluating a process loop, step 1 is to evaluate your turndown requirements, your rangeability. If you need high rangeability, an orifice plate just might not cut it. Step 2 If you decide to pivot to a mag meter to get that rangeability, you have to confirm fluid conductivity. And step 3, guarantee that the physical installation will maintain a full pipe at all times. You really need to lock this relationship into your mind. All right, wrapping things up with section 2. Next up, level transmitters. Let's see how this all builds into our next explainer. Because you see, level is the crucial variable that ties all of these flow dynamics together. I know, it sounds like it should be the absolute easiest measurement in the plant, right? Just figure out how high the liquid is in a tank. But the reality? It is dangerously easy to get subtly, critically wrong, especially the second your fluid density starts to shift. We're going to explore exactly why that happens and how to prevent it in our next explainer. Thanks for joining me today, and keep learning.